Greg Landrum from Novartis. As you can expect, Greg has a background in chemistry and computer science, did his PhD in Cornell, did a postdoc in Aachen, and then started working for a company called Combichem, which was bought by DuPont. And after that, he founded a company called Rational Discovery. I still think you do work along that lines in some ways, right? In your open source work. Yeah. So, yeah, Greg's a big fan of open source. You're partially responsible for the RD kit, but I think that's common knowledge. And he joined Novartis in 2006 in the CAT group, and then last year moved over to IT to become the global head of chemical information systems.
As Medzi said, I'm going to be talking about a new system that we've built together with ChemAxon for searching some historical and ELN reaction data we have in-house. First, I'm going to start with a little bit of context. This is a slide I stole from Anna's deck. It's a reminder of what we're in the process of doing. We're moving away from ISIS and moving to other systems. I will be talking specifically about what we're doing to move away from some aspects of ISIS host. Anna already talked about the first set of these where we're moving databases of compounds into instant JChem. I'll be talking about this last piece, which is moving a historical collection is what this says. It's actually a number of historical collections of Novartis reactions, moving those into a new web application. It's a very rational question of why on earth we would do this, why we're building a new application. Why don't we just migrate the data and search it with IJC, or why don't we just keep using what we have? So first, an explanation of why we're doing this. Here's the current situation. We have a collection of literature and historic in this sense means pre-ELN reactions that are stored in ISIS host database. And those are searchable. People search that from ISIS base. 5 or 6 years ago, we started using the CambridgeSoft, now Perkin-Elmer ELN. Since then, all of the reactions we're capturing are present there. For those of you who understand or who have worked with this ELN, that one of the downsides, or let me start with the positive part. One of the positive parts is it has a very flexible database schema. So you can put anything in it, which is great for them and it's great for people working with them. The downside of that highly flexible database schema is that searching is not really very good on it. It takes a long time to do a substructure search across our ELN database. People do not like that. It drives the chemists crazy. So we wanted to get a system in place so that the chemists could actually do searches of the ELN and get the results in a reasonable amount of time. The rational thing is, since we want to move off ISIS base and we want to provide this ELN data, to put those into one system and to get all of the information that we have, 20 or 25 years worth of reactions, put them in one place and let people take advantage of that body of institutional knowledge that we have. So that's our objective. On the technical side, I'm in IT now. Technical side, there were two primary requirements. The UI had to be web-based, or the UI for searching and browsing had to be web-based, and we had to have web services in the back for searching and retrieving the data. So the web-based UI requirement means we cannot use IJC as the primary interface for this application. I'm going to switch gears for a minute and explain why these two requirements came about, and then I'll go back to talking about what we've actually done. So Anna already showed, these are two things taken from Anna's slides. She mentioned web services already. I'm going to try and say this with a straight face. I haven't been in IT long enough to really be able to do it, but we're placing a strong emphasis on service-oriented architecture and doing things like building an enterprise service bus. I don't actually know what that means, but the service-oriented architecture thing, I think I grasp. Jokes aside, we are making a really concerted, serious effort to get every possible computation service that we have and make that accessible via web service. Some examples, this is not even remotely comprehensive, but some examples of what we have in-house. Anna mentioned this already, that we have web services for querying our new data warehouse. In fact, the application that most people will be using to access that data warehouse is just a thin web application that uses those same web services to query and retrieve results. We have web services for all of our descriptor and property calculations, including QSAR models. We have, and those are all distributed through one central system that I called the cheminformatics framework. They actually tricked me. It turns out that's an enterprise service bus, and when I found out, I was horrified. But okay, it works, so I'm okay with it. The last piece, and this is relevant to one of the presentations we had earlier, you can actually register compounds or biologics. You can access our registration systems by web service internally as well. So the actual registration and, more interestingly, querying. The reason we're doing this, there's fairly obvious advantages in terms of portability. Anything you deploy via web service is instantly global, assuming that you have a network that's capable of dealing with that. We do most of the time. Depends upon time of day. Updates and deployment is really easy because it's centralized. You write the code once, and because it's web service, you can use it everywhere. And the last point I mentioned is mashups. This is something people may know the term from Google Maps. People take applications and take web services and combine them together in interesting and unexpected ways. This, to me, is the real benefit. It's why I put it last. Unfortunately, it's almost falling off the slide. But the idea is if we have everything can be accessed via web service, and we have most of our applications are web applications that are using those web services, the applications can start to interact with each other in ways that we haven't planned for, as long as we have a good API in the back. It also lets us build small applications that are best in breed for a particular purpose. So Dart, the tool that's for doing data analysis and reporting, is a tool that's very good at constructing queries and very good at presenting results in a spreadsheet. It's really fast, it's easy to use. It doesn't have SAR analysis, it doesn't have any of the highly sophisticated features that you would want if it was your only tool. But it's really good at one thing. If we later build a very good tool for R group decomposition, it can use exactly the same services in the back. We can have it exposed in a web application that looks exactly the same as Dart, but it's actually, from an IT point of view, it's a separate application. Easier maintenance, easier UI for people to use, not everything collected in one place. This whole thing, it's the very antithesis of the idea of a one-stop shop. We're going to have a bunch of small applications that are connected to each other and hopefully interacting in interesting ways. Okay, pop out of the aside. We're now going to go back to talk about the application again. How did we reduce this thing to practice? I'm being IT again. So how did we actually do this? Obviously, it was a collaboration with ChemAxon. We started by collecting a series of user stories from within the NIBR scientists. We put together for this a small global team of medicinal chemists. The magic number does seem to be about 7 to 10. We didn't try and get 50 people in a room and reach consensus. There's no way. So we had a small team of fairly experienced chemists who helped work with us to drive requirements for this. We started the requirements, we seeded it a little bit with some of the information that we have from the Pistoia Alliance, the questions that you might want to ask at an ELN from there, together with the experience that people have of working with Cirrus. That's our current application for reaction processing, reaction searching, as well as various other commercial tools. So we kind of mashed all that together, came up with a set of user stories, and then together with Tim, we sat down around a table and spent a day, probably a good day and a half, coming up with the concrete requirements and the design for the application. After all of this, Tim went back and did the implementation together with some outside help, and that's how we move forward. Some requirements on the query side. This is a querying tool, right? The queries are the most important pieces. We wanted to be able to retrieve results based on structure searches. None of this is brain science. It is brain surgery. It's fairly obvious. Structure searching exact and substructure reactants and products. We needed to be able to retrieve additional information for every reaction, so conditions, reagents, solvents, etc. We needed to be able to query across multiple data sources. I mentioned this at the beginning. We have our historical reactions is not one database of historical reactions. Novartis, like all of the other big pharma companies, is a bunch of companies that have been glued together and integrated successfully or unsuccessfully over 20 years. So we have a number of different back-end databases that we need to integrate together. We need to be able to query across all of those, and you want to be able to do the obvious limiting results or limits of your result sets. I'll demonstrate that later. Complexity of that historical data, I mentioned already. There are multiple collections that we have. The idea that we would be able to construct a single schema that holds the historic reactions from SIBA, from Geigy, from SIBA-Geigy, from Sandoz, everybody else that's been mashed into this entity that's known as Novartis. There's no way we could ever do that and have a schema that doesn't look like the Cambridge soft schema, and you could never query. So we said, okay, we're not going to do this. We're going to have a very, very simple query, a very, very simple schema, stores a minimum amount of information, and those are the pieces that you actually need to search and browse the data. All of the additional information that's not immediately needed for searching and browsing the data is just going to be exposed in some kind of get details page that will look different for the reactions from different sources. The standard fields we decided to bring across, obviously the reactions, the date, the chemist, the source, the project, the yield, the solvent, the reagents, and the entity that the chemist was working in. I'll show that in a bit later. Sounds simple. We're going to a simple schema. We're starting from a complex part, and it turned out in order to do this, Tim needed to do a custom RDF importer for every one of these historical sources, and that's actually been, I guess, a fair amount of the work. Has been not writing the web application, that's easy, not writing the web services, that's easy, but getting the data in. This is the architecture. It is the standard approach for a web application. There's a web browser sitting on top of the server that's providing the information the browser gets. There's communication with a service layer. This is the service layer that I'm hoping we're going to be able to use from other systems in order to get these unexpected interactions between applications. Obviously, there's Oracle and JChem in the back, and at some point, we're not there yet, at some point there's going to need to be an application that pulls the data from the ELN and puts it into the Oracle schema and keeps that stuff up to date. Technical requirements, the interface should be HTML5. For those of you who've worked in this space, this doesn't actually mean anything, but it sounds really good. So JavaScript, CSS, and HTML should support a range of browsers. We have at least 2 browsers that are officially supported and a large number that are used unofficially. It has to support, this is a no-brainer, absolute critical, it has to support our internal authorization and authentication framework. The web services, this layer needs to be RESTful, not SOAP, and the ELN database updates have to be automated. So these are the requirements we're working from. The status of implementing all of this, we have a beta of the web interface, which I will show you, beta of the services. The 400,000 historical reactions have been loaded. We're starting to test the application with our chemists next week, I guess, with the acceptance teams that we have in each of our various sites. And we're in the process of planning the migration of the ELN data into JChem. This is, at the moment, about 600,000 additional reactions. It's a big job, and we're still figuring out how we're going to do that. Okay. My original idea is I was going to do a demo, a real demo. And then I thought about, well, live demoing a beta application over Wi-Fi, maybe not such a good idea, but I'll do it anyway. And then I thought about what I would have to do to get that approved so I could do an external presentation where I'm searching our reaction database, a live demo showing it to, but no, I'm not going to do that. So I'm going to do a screenshot demo. This is the basic interface when you start the application. All of our web applications look exactly the same. This is a nice thing for our users. They can't tell which web application they're in most of the time except for the content, and maybe in the upper left-hand corner it has a name of the application. They all have a nice feedback button. You click on this and it automatically sends bug reports or feature requests or compliments. We don't get very many of those, but there is an option to do that. I periodically send them to people on my team just to keep them off balance. On the left-hand side is the query pane. In the middle is where the results are presented. I will show that. And on the right-hand side are filters for the results. For the demonstration, I'm going to do a search for a much used and abused reaction. I'm not doing amide bond formation. I will do Suzuki coupling. So I start by a basic search for boronic acids. As you can imagine, this returns a rather large number of results. I'm not going to show all of them because there's no way I could get that approved. I'm doing strategic blurring in here. I apologize for that. So I do the search, and after a short period of time, it comes back, and it shows me the results oriented like this. If it's the same reaction run under multiple conditions, they're shown here. I can click on the individual piece here and get details about that reaction. The right-hand side, I have the filters, so I can expand those and say, well, at the moment, there are 5 different collections present. There is the Novartis backlog. There are 2 different SynLab tabs. These are the scale-up labs. These are the ones that people actually typically want to see the reactions for because they tend to be the most reliable. And then there's 2 other historical collections. What I did here is to try and find the interesting Suzuki coupling out of the thousands that this returned. I started with doing just the ones from the scale-up lab, to hope that those would be more reliable. I still had too many results, so I went back to refine. On the left-hand side, what I've done, sorry, this doesn't show up very well. The left-hand side, I've said, okay, only show me the reactions that have at least 80% yield. I still got too many results, so I further filter. I have my SynLab checkboxed and gone through and turned off things like I don't want to see the things in dioxane. So this is not actually a useful demo, right? The idea is to show the application itself. Remember, left-hand side is query. Anytime I change anything over there, it executes another search. The right-hand side, these are just filters. These are just changing what's visible without repeating the search, so it's really, really fast. So if I want to toggle between sets, that goes very, very quickly. That's the application. It's a short demo, right? This is a very simple application. The intent is that it be very, very simple. We're not doing anything complicated as far as the user is concerned. There's a lot of complexity in the back end to make this work, but for the user side, it should be really, really simple. All we're doing is searching reactions, showing them the results, and letting them filter the results down to find what they want. So what's next here? We want to get the application out to those test users and start collecting feedback from them. We need to get the ELN data loaded. This is critical. We need to start thinking about better ways of organizing the results so that when you do the Suzuki coupling query and you get back the thousands of results, you can actually kind of group them in a somewhat more logical manner. I'm really keen on this connecting to other web applications piece, right? So starting to have these applications talk to each other. You can imagine just sitting and kind of making things up. I have this web service layer that provides me reactions. I can do substructure searches there. I have this other web interface that pulls results back from our data warehouse. I could easily imagine adding a link into that. So I get a result from the data warehouse, I click on it, and it takes that product, or takes that compound and does a product search for it in the synthesis table. Or maybe it actually plugs that into the reactants thing in a synthesis search, so I can find ways to derivatize that compound, or ways that we have derivatized that compound. There's a lot that you can think about that we're going to get for free because of the architecture, because of the way this stuff has been built. And then, because we haven't started talking to the test users and collecting feedback, there's rather a large number of question marks down at the bottom as to what comes next with this application. We're going to start collecting that next week. So, acknowledgements. Our test users within global chemistry are on the left. The people in IT who helped us on this, particularly the DBAs, who've been very helpful in getting the database infrastructure set up to make this work. And then ChemAxon and the guys they're working with to do the implementation. And finally, I'd like to thank you for your time.
Once you've integrated the electronic lab notebook experiments, is it your intention to have a single click back to the ELN so they can see the whole thing?
Yeah.
Yeah, you think that'll be straightforward?
We are already providing to go to the ELN itself, not. We have an application already connected to a web service that constructs a synthesis sheet. So it pulls all the linked ELN experiments and constructs a single synthesis sheet that people can use. We're going to link to that. That is straightforward because it already exists. Building that was not straightforward.
How do researchers actually store and share their results in this web application, from this web application?
That's a good question. And I will defer to Anna and Tim to answer that question because I don't have an answer. It's bookmarkable, the results, right? Yeah. the idea, most of our web applications are bookmarkable. So if you do a search, you can bookmark it and then just save that, email that to someone else, and they'll get the same results back. We haven't started talking to the users yet. So we're starting with a very, very simple application. And when we start gathering the requirements, if there comes a requirement for doing exporting, we will add it at that point. We didn't want to preload all the features and then have it turn out that people are not interested in them.
Actually, two questions. First is, do you have an ontology for the reaction conditions, so standardized ways to characterize catalysts? What happens if there's mixtures of weird organometallic compounds? And the second is, do you include failed reactions, so processes that did not yield at the given conditions?
The failed reactions is yes, and the ontology or standardization of reagents, catalysts, et cetera, is no. We don't even have rules for what language the ELN has to be entered in. So we have, you can imagine historical reactions. Certainly we have a mixture of German and English. Going forward, we will continue to have a mixture of German and English. We are not standardizing those. What the hope is that if we provide people with a useful search and useful filters, in ELN there is an option. People have controlled vocabularies to pick those things from. They don't have to, but we hope that they will start doing that because they will see a benefit, because it will make this tool more useful. We cannot impose it on them because they would strangle us.
Just a quick technical question. What was the main reason for selecting RESTful services instead of SOAP?
Interoperability. So calling SOAP services from other web applications is a real hassle unless you're using you have to take your JavaScript framework and make sure it speaks exactly the same SOAP as whatever the backend is doing. And then we have people using Python, we have people using .NET, we have people using Java. SOAP interoperability just doesn't work. So the RESTful piece it's so simple that it almost cannot not work.